When you think about how we build amazing things like cars and airplanes, you probably picture sparks flying, right? Metal fusing together. But what's really wild is that nowadays, a lot of the real work happens long before that, inside a computer. Engineers are actually designing the perfect aluminum weld before anyone even thinks about lighting a torch.
And that brings us to the big question for today. How on earth do you perfect something so physical, so intense, as a weld, but in a totally virtual space? Well, it's a huge challenge for sure, and the answer lies right at the crossroads of materials science and some seriously powerful computer simulation. So let's dive in and see how it's done.
All right, here's our game plan. First, we're going to tackle why welding aluminum is so tricky to begin with. Then, we'll take a trip through the evolution of computer models, starting with the big picture and then zooming all the way down to the microscopic details. And finally, we'll look at what this all means for the future of, well, how we build everything.
Okay, so aluminum is an incredible material. It's light, it's strong, it doesn't rust, it's a wonder metal. But, and this is a big but, when you get to the super high-strength alloys, the kind they use in aerospace, joining them together is just notoriously difficult. They have this nasty habit of cracking. And this problem has a name. It's called hot cracking. Basically, as that molten pool of weld metal cools down and shrinks, it's put under an insane amount of stress. And if that stress builds up faster than the metal can get strong, it literally just tears itself apart. It's a high-stakes race against time, happening at a microscopic level. So, how do you stop this from happening? I mean, you can't see the stress building up. This is where engineers turn to computers. The idea was to create a sort of digital weather map for the weld, one that could predict where these high-stress storms were most likely to pop up. And check this out. This is how it works. On the left, engineers feed in everything they already know. The exact chemical makeup of the alloy, the shape of the part, even the path and the heat of the welding torch. Then the software, in this case it's called WeldSim, it just crunches all those numbers to predict what's going to happen on the right, the temperature, the distortion, and most importantly, the stress. What you're looking at here is that whole process in action. It's like a domino effect. First, the model calculates how the metal's internal structure changes with the heat. That calculation then tells it how the temperature is going to spread. That temperature flow is what causes the part to warp or distort. And it's that distortion that creates the final stress that could cause a crack. See how it all connects? The magic behind all this is a technique called the finite element method, or FEM for short. The way it works is, it takes a really complex part and digitally breaks it down into thousands or even millions of tiny, simple little pieces called elements. Then it solves the physics for each one. It's amazing for seeing that big picture, that weather map of where the stress is likely to build up.
But, there was a problem. A big one. These big picture models, they could tell you where a crack was probably going to happen, but they couldn't tell you the most important thing, why it was happening. There was a deeper mystery that needed to be solved.
So what gives? Well, FEM is fantastic at predicting those big, high-stress zones, but it's completely blind to what's happening on the microscopic level. Down at the scale of the metal's individual crystals, or what we call grains. It just couldn't see the tiny little events that were the real culprits, the things that were actually starting the crack. And this quote from a research paper just hits the nail on the head. The very thing that makes these big models work, the fact that they simplify things, is also their greatest weakness. The assumptions they have to make mean there's a hard limit to how accurate they can ever really be.
So this begs the question, right? What exactly are these big picture models missing? What is going on down there at that tiny microscopic scale that makes all the difference between a perfect weld and a total failure?
The answer meant we needed a whole new kind of simulation, one that could zoom in, way in, from the scale of the entire part all the way down to the level of individual metal crystals as they're literally being born out of the molten weld pool.
And this is where a seriously cool technique called phase field modeling comes in. The best way to think about it is like a biological simulation, but for metal. Instead of just calculating forces, it actually simulates the growth of the metal's internal structure, how those individual crystals grow, branch out, and lock together as the weld freezes solid. So how do you get these two very different models to talk to each other? Well, this workflow lays it out perfectly. You start with that big picture weather map simulation to get the general heat conditions. Then, you zoom in on a tiny spot you're worried about, and you pull out two key numbers, how fast it's cooling down and which way the heat is flowing. You take those two numbers, and you plug them into the microscopic phase field model, and that's what tells you how the crystals will actually grow in that one specific spot.
It's a really clever way to connect the huge scale with the tiny details that really matter.
So all of this mind-bending computational power, it leads to a massive payoff. We're talking about a shift from just trying to predict failure to being able to actually design for success right from the very beginning.
This is what virtual manufacturing is all about, and honestly, it's a total game changer. The goal isn't just to check if a design you already have is going to work. The real power here is using these simulation tools to invent completely new materials and new processes, all inside the computer, before a single piece of real metal even exists.
And here is a perfect real-world example of that in action. Look at this chart. Alloy 1, that's a standard aluminum alloy. It welds great, but it's not super strong. Then you have alloy 5, which is a traditional high-strength alloy, but its weldability is terrible. It cracks. But now, look at alloy 4. Using these advanced models, researchers were able to design a totally new alloy by tweaking the ratio of zinc to magnesium. And the result? An alloy that has both high strength and good weldability. That's something people thought was basically impossible.
So let's wrap this up. We've seen welding simulation go from these broad weather maps of stress all the way down to simulating the growth of individual metal crystals. These incredible phase field models don't just tell us where a weld might fail anymore, they show us the fundamental reasons why. And that deep understanding unlocks the Holy Grail, the power to design brand new, amazing materials, literally from scratch. And that leaves us with one last big thought. For decades, the designs of our most ambitious projects, planes, cars, you name it, have been limited by what we could reliably stick together. But now that we can design the material and the weld at the same time, in a virtual world, what new things can we finally build?